Suppose that there do exist integers p and q such that root 2 is equal to p over q. We also assume that p and q have no common factor, since if they did, that common factor could have been cancelled out. So p over q is in its lowest form. Now our argument is in 3 simple steps. First, we square this, so we get 2 equal to p square over q square, which means that p square is 2q square. So the right side is 2 times something, so it's even, which means that the left side is even, which must mean that p itself is even. So p is even, so we write it in the form 2 times some number m. Now we substitute this 2m back into this equation, so we get 2m whole squared is equal to 2q squared, which means that q squared is equal to 2m squared. Now what do we conclude from here? This right side is 2 times something, so that's even, which means that q squared is even, which means that q itself is even as well. So q is of the form 2n for some natural number n. Alright, so now our third step, we just observe that p is of the form 2m, q is of the form 2n, and therefore p and q have a common factor of 2. But we assumed that p and q have no common factor and p over q is in its lowest form. So that's our logical contradiction right there, and the only thing that can mean is that this assumption is incorrect. There are no integers p and q such that root 2 is equal to p over q, which means that root 2 is irrational. Now can you use the same method to prove that root 3 is irrational?